Okay, so let's start. So I'm cheated a little bit to write these things that we did yesterday. So today I'd like to concentrate on the Brakke's mean curvature flow, which is unit density also. Okay, as I said yesterday, unless it's unit density, the regularity theory, even for stationary or static situation, is not so much well understood. So I might as well just concentrate on a unit density case, meaning the density multiplicity function is equal to 1. So just if I concentrate on that situation, okay, of a unit density Brakke flow, so I just wrote what I wrote yesterday more or less, except that for almost all time now, this varifold, yesterday I just said this is integral varifold, but since I'm assuming it's unit density, multiplicity function is 1, so that means that there exists a measurable can't-be k-rectifiable set, MT, which gives you this VT in a way that's very natural, as the one that I explained on the first day. Okay, so that this induces a natural varifold, VT. And also notice that in that case, the weight function, or weight measure, or mass measure, is nothing but just k-dimensional Hausdorff measure restricted on MT. Okay, so that's, please interpret this, whenever you see this, it's just this. Okay. And the number 2 was for almost all t, the first variation of this guy is locally bounded and also absolutely continuous. Okay, that's exactly the same as yesterday. So meaning this means that there exists the Radon-Nikodym derivative, which I interpret as a mean curvature vector, okay, as a generalized sense. Okay. And the third is that this mean curvature vector is L2 in space-time, which is something that is naturally expected when we are looking at these things, because the way we define the velocity of this motion of this varifold is formulated in this way. That is, given any non-negative, that's very important to remember. This non-negative test function has to be non-negative, at least C1 say, depending on x and t. And so this is sort of an integral formulation of what we discussed yesterday. That is, for any t1 and t2, the integral over phi evaluated at time t1 and t2, the difference of that is bounded by the right-hand side, which is at the derivative of t and the number of phi minus phi h dotted with h is above, okay, this left-hand side. And I notice that as you see, this here is h dot h term, which is h square, and unless this guy is finite, well, is integrable, L2, you kind of have problem here. So from the nature of the problem, you do expect this has to be L2. Okay, so you get that as part of the existence theory usually. Okay, so today first I actually didn't state what the regularity theory is. Yesterday, so let me write the. So this is a theorem. Theorem. So this is, as I yesterday explained, it's originally claimed by Brakke, but it was not quite complete or wasn't too much understood for years. So, but I still give credit, of course, to Brakke. And also fairly complete proof is given by Tonegawa. It's a 94. This paper is the one that I listed as a reference in the abstract. Okay. And also, by the way, this one is a C1 alpha regularity theory, and the other one, also this 14, is a C2 so the C2 beta and C infinity result. And maybe I should add Lahiri's work on this. So maybe I should also say Lahiri. Okay, so this is, well, Lahiri's work is, by the way, is up to C1 alpha. And you may think that once you get C1 alpha regularity for elliptic case, you are sort of done. But in this case, it's actually not so easy. In fact, even if you get C1, well, I don't really want to talk about this too much, but there's actually step that you have to prove going from C1 alpha to C2 alpha. That's non-trivial, in fact, and that's what's done in this paper. Okay, so let me state. So suppose this Vt, say from let's see 0 to t, is unit density Brakke's mean. Let me write BMCF. Brakke's mean curvature flow in U in Rn. That's open set. Then what you can prove is that then they exist. Sorry. So for almost all time, okay, for almost all time, there exists a closed set. Let me write this as a let's see, maybe Ct in U, which has a measure 0, k-dimensional measure 0, and also with the following property. Okay, so basically what I'm going to write now is that so this CT is a singular set, okay, singular set, and outside of that, things is smooth. That's basically what I'm going to write. So since there's a space-time variable, it looks kind of slightly messy, but all it says is it's regular outside of that set. So for any point outside of this singular set, there exists R which depend on x and t such that this set, say t, let's see, t is from, say, let's see, t minus r square, t plus r square of support of vt prime cross t prime, which is a set in u cross 0t. Okay, so that's more like a history of this motion, okay, in space-time. I hope that makes sense. I mean, this is more like, so suppose this is Rn is a time. Then you see you have a sort of motion. And so this is a sort of a space track of this motion. Is either empty or C infinity k-dimensional mean curvature flow in Brx cross t minus r square t plus r square. Okay. There's the option of being empty, of course. There's nothing there, but So what it says that for almost all time, you look at the point, then there's a neighborhood in space-time. There's a neighborhood in space-time. Inside this support of, this motion of this measure, the support is a smooth or empty. There's nothing, or it's a nice smooth mean curvature flow. So you might say this is almost everywhere, almost every time regularity. Okay. For almost all time, there's a singular set, measure 0, and for each time size, everywhere, almost everywhere, it's regular in space-time. So that's what it's claiming. Right, and notice that so the first remark is that, well, of course, if Bt is just static, okay, static case, then that reduces to the Allen regularity theory. That is the one that I explained yesterday. That is, if it's static, then that means, well, maybe it's not so clear, but actually, if it is static, then it automatically implies, well, this may not be so entirely clear, but actually, you can prove it. You can prove that the mean curvature has to be equal to 0. That's something that may take some time. Getting out from number 5, you can actually prove that the mean curvature has to be equal to 0 if it stays static. Okay. Then that means this reduces to the situation of Allen regularity theory. Well, I actually haven't explained what the Allen regularity theory, so I'm kind of addressing this to someone who knows about this. But so I'm sorry about this, but let me just I can do this regularity theory. So this theorem does include, in fact, in a strict sense Allen regularity theory. So it's more like a parabolic generalization of Allen regularity theory. And so again, let me just address to people who may seen the regularity theory of Allen. Allen regularity theory, just as a remark, another remark, is that in fact Allen regularity theory is a theory for varifold with mean curvature in, so Allen irregularity theory is for the one that mean curvature is not necessarily equal to 0, in fact. As long as mean curvature is in LP with respect to the surface or mass measure, okay, where P is strictly bigger than K, which is a dimension of the varifold, okay. Allen regularity says that if this is the case, then it says, and also I'm assuming the unit density situation, then the sort of same, so it's almost everywhere regularity except that in case h equal to 0, you got real analytic smooth surface outside of a singular set. But if you have this, just only h being in LP with respect to the mass measure, okay, maybe it's not so clear, so let me just say. So that means HP dV, is, well, locally at least finite. That's what it means. Then almost every regularity, and the regularity of the is actually C1 1 minus K over let's see, P, I guess, yeah. So that's the so you can show that outside of a singular set, the surface is actually C1 1 minus K over P Helder class. Okay. Now what we proved is really strict generalization of this statement too. Even though I don't discuss this and I stick with the simplest case of Brakke's mean curvature, so I just mentioned that in fact what we got is the situation where v is equal to h plus some extra term, which you have to project to the normal direction. And the assumption you can, well, so under the assumption that this u is in LP dvt p over q dt. If this is finite, okay, so instead of considering just a mean curvature flow, but the one with mean curvature plus some extra term, with this extra term satisfying this kind of integrability condition with condition that 1 minus k over p minus 2 over q is bigger than 0, then we get, in fact, instead of the smoothness, we get almost everywhere C1, let me call this number as alpha, C1 alpha regularity. So that's actually the full statement of the this Kasai-Tonegawa's paper. So you see that, notice that if it's static, okay, if it's static, you can take Q to be infinity, and this becomes 0, and this actually reduces to this situation somehow. This means it's 1 minus Q over P is bigger than 0. Right? So so this is so that's actually the full statement of the regularity theory that we proved. So and it's actually kind of interesting that how the this parabolic regularity theory corresponds to this Allen regularity theory. Somehow Allen regularity theory assumes that the mean curvature is LP, p bigger than k. Here it's a bit different. You see, you are not assuming that the mean curvature is any higher integrability class, but only L2. What you're assuming is integrability on this this kind of extra inhomogeneous term with this kind of condition. And if it's static, that means b is equal to 0. And more like, as a result, h is equal to minus u, and u belongs to this class. So h, as a result, become sort of satisfying this condition. So in a way, I find it kind of interesting that this is the way you can interpret this Allen regularity theory. Somehow, a priori, you kind of assume that mean curvature is in this, but with this kind of point of view, H is kind of balancing this outer field, and the outer field is in this class. Then, as a result, you have this mean curvature in the same integrability class. So, in that sense, I thought that's very interesting. Okay, and also I should have the other third remark is that this result can be extended. This result can be extended to the Brakke's mean curvature flow in general Riemannian manifold. Okay, so you can define Brakke's mean curvature flow in a very natural way to the Riemannian manifold. Okay, in a general Riemannian family, you have extra. If you know about these kind of things, you remember that you get some extra term coming from the. Oh, sorry. If your Riemannian manifold is embedded by isometric embedding by Nash, then well, you can think the flow as some flow in the Euclidean space, and then if you think that way, then you get some extra term coming from the second fundamental form of this embedding. And but anyway, you can define such things Riemann manifold. And so in the second paper, I discussed this, but also we have this the same kind of almost everywhere and almost all time regularity for this setting. just like Euclidean case. Okay. This, I think, was not known, at least at all. Okay, so that's a statement. And the proof is quite long, in fact. And, but I can't really explain the whole thing. But I'd like to at least give you some kind of key points, how one gets these kind of things in the end. You see, when I first saw these things, and when I first saw, heard the Brakke's theorem, I thought that's quite amazing. You get this inequality, which seems to be kind of, I mean, it seems like it's hard to relate this to regularity theory in some reasonable way. It's very different from saying mean curvature 0 and this. Such a jump. And since it's defined by inequality and you still get this regularity theories, to me was very amazing. And so I think I'd like to at least convince you that there's some of the first steps that you can do get this regularity theory. So, but before I do that, I also want to explain the local epsilon regularity theory. So this is actually the key step. So this is local epsilon regularity statement. So to do this, I need a bit of a notation. So let t to be t I just used as a time already, but from now I'm sorry. Let t be a plane, k-dimensional plane. Okay, sorry, this t is not time anymore. Okay, so capital T is t, and also just for simplicity, I can identify this t to be Rk cross 0 in Rn. Okay, so that's easy to visualize. And let's see Tr to be a cylinder, which is orthogonal to T and radius R. Such that T of x is less than R. Okay, so if in the case of n equal to 3, this is T, and like that. And this CTR is the cylinder, which is perpendicular to T. Okay, something like that. This is CTR. Okay. And let's see what else. So, this T is so it's if you think this T to be a projection map to this plane, and also T perp is the orthogonal projection. This is well, maybe I should add 0 here, but I hope you understand this. Okay, maybe I should add 0. Sorry. So that's 0, xk plus 1, xn, which is t perp. Okay, and also I need to define a couple of other things. Let phi is a function on Rk and R be smooth approximation radial, smooth radial, I should have said smooth radial approximation of the characteristic function of ball of radius 1 in Rn. Okay, so this is actually k-dimensional also, right, so it's just that it's the usual -1 to 1. Okay, so it's just some kind of smooth approximation of characteristic function of ball radius 1. And then I define phi t of x, which is a function defined on Rn now, let phi t be defined as the so this function is defined as a phi t of x is phi of t of x. Okay. So you project it to t and then plug into here. So by definition, this is more like the approximation of a characteristic function of this cylinder, if you think about it. Okay. So that's what we need. And also, let's let omega k tilde to be defined as the, let's see, this is the integration over t of phi t of x squared, thk. Okay. So that's really more like it's, you know, this is like this phi is a characteristic function, and so this number is very, very close to the unit disk, volume of unit disk. That is okay, because this is this. So this is roughly the let's see hk of ball of radius 1. Okay, k-dimensional ball of radius 1. Okay. I need this kind of a little bit smoothed out characteristic function. Okay, it takes time to even define these things, but okay. So here's a statement of the low coefficient regularity theory. So suppose the following is the claim. Given, okay, so the statement of the theorem is suppose given number nu between 0 and 1, and also E1, so, and well, I guess I just take n and kb also some number. Okay. Now there exists epsilon, which depend on these numbers only, n and k, which is between, say, 0 and 1. This is supposed to be a small number. Okay, positive but small. And also there exists lambda, capital lambda, which also depend on this number. And this number is actually a big, relatively big number, but not extremely big, I would say. Let's see. So this is some number with the following property. Okay, so I give nu E1 and well, dimension. Well, you can probably think this as sort of constant, but anyway, so maybe you can forget about this. But anyway, nu E1 and lambda with the following property that suppose we have the Brakke's unit mean curvature flow. Unit so assume that, let's see. So suppose this Bt. Now T goes from minus lambda to lambda, okay, is unit density brackets mean curvature flow in cylinder CT2, say. Okay, so it's a little bit bigger than 1, so it's 2. And assume that there are, say, 3 conditions. Okay, one is assume that V at near the initial time. Okay, so the time is minus lambda but plus 1. Okay, and then you measure, well, you measure this t square. Okay, so remember this, you have this function here. So this one is less than 2 minus nu of this omega k tilde. Okay. So let me just finish writing. Number 2 is the B at close to the end. This one is bigger than nu times omega k tilde. Okay. So these are the assumptions. And the third is this quantity. Let me define this as L. This number is minus lambda to lambda dt. And in the cylinder, you integrate this function. Okay, take a square root. This is less than that number epsilon. Okay. So that's the assumption. Oh, I'm sorry, another one. Yeah, sorry, the last one. Well, you can see that I can't really present this kind of theorem unless it's a course. Yeah, it takes a really long time. So number 4 is, let's see, so for any bore radius r inside of the cylinder, we have this mass ratio bound is less than equal to E1 r to the k. Okay. For I guess for any t. Yes.
I think the 3.
Yes.
See any information coming from
Sorry, that's right. Yes, thank you very much. Yeah, because this is VT. Sorry. I misunderstood. Yes, sorry. So that's integrating with respect to this moving measure. Okay. The conclusion, now that's it. Conclusion. Conclusion is that then we have this support of Vt with the intersection of cylinder radius 1, say where t is say between minus 1 to 1, so near the center in space-time is in fact smooth. Okay, C infinity graph over the t. Say maybe I should say graph of f dot t or something. And with the estimate, so that also comes with estimate. I think this kind of estimate I think is perhaps more useful than the partial regularity results, in fact. But so this is a smooth graph, And then also this f xt, this f, any derivative can be bounded over this. Let's see, -1 to 1. This is bounded by any Cj derivative is bounded by constant, of course, depending on J, mu E1, N and K times L. Okay. So all derivative is bounded in terms of this quantity L. Okay. So that's the full statement of epsilon regularity. Okay, so first maybe I should mention, okay, now if this does not depend on time, it's actually Allen regularity theory. If you have seen Allen regularity theory, you really notice the similarity between the Allen. But anyway, so maybe I should jump into that, but maybe I should give a motivation to, let's see. What would be this moment? Right. Okay, so let's see. So first, maybe I should say that all these. Oh, by the way, number 4 is somehow number 4. So the remark is that number 4 is usually is assumed, but in fact, actually, this kind of estimate comes from so-called Huskins monotonicity formula, and in fact, you don't really. I assumed it just to get this number E1 to be very how to put it to make it explicit, but in fact that E1. Actually, I don't have to assume this. This follows more or less for some E1, in fact. Yes, yeah. Okay, maybe it actually can be dropped with suitable modification of the statement. Can be dropped. So this, I'll get to this this afternoon, I think. But here's monotonicity formula. Okay, so that's one. But these 1, 2, 3 cannot be suddenly dropped. Okay, so let me explain why. So number 1, the necessity of this assumption 1, is because this is roughly saying that toward the beginning. Okay, so this is minus lambda plus 1 means so if this is a time, we have this minus lambda to plus lambda, and so that's somewhere here. And so the number 1 says that notice, remember this is like the characteristic function of the cylinder of radius 1. So this is saying that, and so this is saying that you don't have like 2 disks, 2 planes. Okay. So the number 1 is saying that, okay, so here's the cylinder. So I don't want the situation where there's 2 flat planes. Okay, 2 flat planes like this. You see, plane does not move. It's just no curvature. Okay, so if you have these 2 planes very close to say T, there's no way that you can represent this guy as a graph, as a single graph. Okay, so to exclude this kind of situation, I'm putting this condition. Okay. If you have this cannot be possible because this is going to be this is going to be like almost 2 omega k tilde. Okay, so then in fact Allen's regularity theory you have the same kind of things here as well. Okay, so that's somehow expected, and the number 2 is also necessary because so number 2 is also necessary because the point is. As I explained yesterday, this Brakke's law can just vanish right away, at some point, may become 0. Then it's empty. And there's nothing to prove in that case. Actually, you don't have anything. Okay? But if you assume this, number 2, so toward the end, at least you have something. Okay? So you don't allow that happen. Okay? So but unless you assume this, that's a possibility. So this number 2 is also necessary. And the number 3 is the sort of very weak condition that this varifold stays very close to t in space-time. Okay? Because notice that if this, so this, notice that what is t perp of x square of dvt? Okay, so if this is already a graph, if we know that, okay, so let me just assume k equal to -1, okay, just to have a mental picture. Then this means that this is, if this support is represented as a graph, okay, if support of bt is already a graph of f, then what this is that, and also assuming that the t is the r n minus 1, okay, then this is what this is really let's see, bow of radius 2 with n minus 1 dimension of fx square, because the t perp is how far you are from this plane t, right? So how far you are from t is given by this number, and then you are integrating this t square, and maybe you have an area element, so 1 plus number f square dx1. That's what this is. You're integrating in time also. So this condition is in some sense, very roughly speaking, like smallness in L2. Okay, distance L2, maybe I should say distance L2 to the plane. Okay, so this is saying that if L2 distance is small, sufficiently small, if you have these two conditions, then it's regular. Okay. So and if you know about Allen regularity theory, this is exactly what's done. So that's a statement. Okay, so now let me explain. Maybe should I take a break now? Maybe a few minutes. Yeah.
Distance from
T. Yes. Yeah. T perp is T perp x means really how far you are from the. So I can replace this if you like. I can replace this by it's exactly the same thing actually. Distance of x to t square. That's exactly the same thing, really. Yeah. So it's more like L2 distance. Yeah. Yeah. Okay. Maybe take a break, but yeah. But okay, maybe just.
So, if you think of Allen, what
Yeah.
he puts in there is the oscillation of the tangent plane.
Right.
Which is kind of a derivative of this.
Yeah. Well, you can also write in this way too. Yeah, Allen's, because that quantity. Let's see. Yeah. Okay. Yes.
So, sorry, this is going to be a very technical question, but if you replace your
Yeah.
oscillation of the tangent planes by these,
Mm-hmm.
I know that in the long run the thing that you control is that, but somehow, at least in the proof, there's a place where you need the oscillation of the tangent planes. Do you
Yeah.
have
But
a proof where you can go?
But
You
even
can do without the oscillation of the tangent planes and just use these numbers?
yes, but even for Allen, that quantity is bounded by L2 distance too. But yeah.
I understand that.
Yeah.
So
but
that quantity is
yeah.
bounded by the oscillations of the tangent.
Yeah.
The oscillations of the tangent is not. You need to assume something a priori on the oscillations of the tangent to prove the oscillation of the tangent is bounded by this guy and
Yeah.
and something having to do with age.
Okay. Yeah, I guess. Yeah, you could you can work with the oscillation too here. In fact, it's almost equivalent. Yeah.
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 No, but so my question is,
Yeah.
I remember asking Leon a couple of years ago whether you could do everything in Aller, just forget the oscillation of the tangent.
Yeah.
Just use those quantities.
Right. Right. I see. Well, I have to use.
And I just was
Yeah.
wondering if you really, if at least in this case, you really just use those quantities and therefore you never go through those. I mean.
Yeah. No, you do use it a lot actually. But the thing is, you can bound this guy by this L2 distance and the mean curvature square. So there's sort of interpolation that you can do. Yeah.
But without having to assume a priori that the oscillation was small, the oscillation of the tangent was small, because that's how you do it now.
Right, right, right.
If the oscillation of the
Actually,
tangent
it's
is
true.
small, then you can bound. But if
Right,
you
right.
don't, then
I guess here you
can't.
don't, in fact. Yeah.
Okay.
Yeah. You get it as a result more like. Yeah. It's actually one thing you have to prove. Yeah. Okay. Let me start again. So, I'd like to explain some of the well, actually, the C1 alpha regularity theory is about 60-some pages. So, it's actually fairly long. And by the way, this Kasai Tonegawa paper, I actually made a serious effort to be readable, very readable paper. In fact, I asked my master students to read it, and he managed to read it. So I think it's not like Federer's, paper where it's very hard to read and all. So I mean, and you can actually also learn about how to prove Allen regularity theory at the same time, even though it's much harder. But so I mean, I don't want to advertise too much about my paper, but I think that's not a extremely bad paper to read. So, okay. So number 4 is just let me give you an idea of proof of epsilon regularity. So, by the way, epsilon regularity, once you get this epsilon regularity theorem, getting a partial regularity is not as easy as Allen's case, that is time-independent case. Actually, it's fairly complicated to get this epsilon regularity to partial regularity. There is some fair number of steps, but anyway, this is a main part in some sense. Once you do that, then there's way to prove partial regularity. So now, so what I'd like to explain is basically what we have in hand is really just one inequality, right? That's number 5. This I guess it was here. Yeah, this inequality is the only one we have in control. Okay, so we have to do everything with this, nothing else. Okay, so you have to play with this a lot, and how? So one, I think everybody probably knows that one important kind of step to get a regularity theory is, for example, in case of harmonic function, some of the important, or the something elliptic nature. One of the things that you need to get is so-called, say, Cacciopoli type inequality. That is, you kind of get a bound of the derivative in terms of the, let's say L2. But maybe you pay for the gradient of test function. Something like this is essential to get a better regularity. I mean, just very philosophically speaking. Okay? And you want to have something like this out from this inequality. Okay, so that's what we try to do. So, so the first step is, so let me just say this is a, say I just might call this as a Cacciopoli type. Estimate. Okay. So how do you do this? So let me write as a proposition. This is actually corresponds to my paper, Kasai Tonegawa 5.2. Okay, so this I would say it's more like geometric Sobolev inequality. I like to name this as force. Well, this is implicitly written in Brakke's monograph, even though it's kind of hard to see where it's there. It's in that book. So it's very, I think, kind of interesting geometric things here. So suppose that V is this. Okay, so now this guy has nothing to do with time. Okay, so let's forget about time. So suppose varifold comes from ambient M. Okay, and suppose B is this, and also we set alpha to be L2 mean curvature with this phi t square. Okay, cylinder. So let's say this is L2 of mean curvature, and let's say let's see, this is it, and let C to be L2 that I just explained, C2 of t. As I said, this you can think as a distance to t square. Okay. This without phi t. Okay. And also assume that we have the same bound that V of Vrx, Vrx is bounded by Rk E1 for any ball inside of cylinder. Okay. Then the statement is the following. So then there exists this small number C1, this is in 0 and 1, and also there exists alpha 1, also a small number, 0, 1, and also a constant, which is big, typically, depending only on depending only on nu E1 and Nk, such that following, let's see, why is it depending on nu? Let's see. Yeah, sure. Okay, so that such that if so, there's two possibility here. So the number one possibility is if this Xi, this L2, is less than Xi1, this small number, and also L2 of mean curvature is less than alpha 1, and also another one, omega k tilde, which I defined before, minus this phi t square dvt. So that's like that's how much you have in the cylinder of radius 1. Is less than well, I'll explain what this means. Actually, 8 is not important, but this number is less than omega k. Okay. Under these three assumptions, then we have the following estimate. Then this cylinder phi t square dvt, no, t. Sorry, there is no time, so here's no t. Okay. This is sort of independent of time. This difference can be bounded by, so depending on the dimension, this is constant times alpha 2k minus k minus 2 plus alpha 2 over 3 xi 1/2 plus xi square. If k is bigger than or equal to 3, and c times alpha 3 over 2 xi 1/2 plus xi square if k is either 1 or 2. Okay, so that's one possibility. And the second option, second possibility, if xi is less than xi1 and the following inequality is true. let's see, this is bigger than omega k tilde minus okay, this is between these two numbers. Then the answer to the last commutation is this is less than bigger than alpha 1. Okay, so that's the statement. It's very long, sorry, but let me explain what this is. Okay. Yeah. Nu is sorry, yeah. Nu is some number between 0 and 1. Okay. Yeah. Yeah. Okay, maybe I had this.
So C2 is in T is your A plane and 2 is your theta. So C2 is T, the plane, and you have a...
No, you have a CT. T is this. Yeah. This is CT2 is a cylinder with radius 2, like this. Okay. Yeah, yeah. So the idea you should have in mind is, so here's T. You know, this is a plane. And then CT is the cylinder, and then this manifold. Well, this support of this guy is like some sort of surface which looks like this. Yeah. That's the sort of picture you should have in mind. Okay. Okay. So let me explain what this is. So this, suppose you have these guys now. Then. So let's consider the you see, first of all, notice that this quantity this is not this what this is the amount of area inside this cylinder. But notice that this is a characteristic, almost like a characteristic function of cylinder 1. So inside of the cylinder of T1, okay, right? So that's the amount of area inside of this cylinder. And the first assumption is saying that, well, assume that this L2 distance, yeah.
The same cylinder, CT.
Oh, yeah. Sorry, this CT.
Because the P is okay.
You have this guy, and you know this is like a characteristic function of cylinder of radius 1. Okay. Right. Okay. So the number one option is suppose this C is small. You know that guy L2 distance is small, and also the mean curvature L2 is small, and also here is what's saying. So the amount of area inside the cylinder, and so you see if this guy is totally flat, okay, if this B is totally flat, say equal to T, then of course this guy is equal to this phi T square dVt. dV is precisely equal to omega k tilde. Okay. Now, so this third condition is saying that, well, the area is not too far from unit disk, say. Okay. At least that much, say omega k over 8. So maybe I should draw a painting picture. Here's the omega k. And here's 2 omega k tilde. So the third condition is saying that your area inside of this cylinder is somewhere between here, okay? Here, in this interval. So that's the situation. So yes?
Omega k tilde is not the measure of the unit wall in RK, but the measure of the unit wall, like with this speed in it.
Yeah. Yeah, you can really think, well, you know, I need to introduce this sort of smooth out guy just to carry out the other arguments. But you can really think this as a sort of characteristic function of cylinder of radius 1, if you like. Okay? You can think that way. Yeah. So maybe it's easier that way. So this is saying that the area inside of the cylinder radius 1 and then the unit disk, that's not very far. Okay? So if that's the case, the conclusion is that the difference of the area and the unit disk is bounded by the right-hand side like that. This is that as you can see, yeah. And the next option is saying that if L2 is small, and if your area is in that range, so what is the range? That range is, in fact, it's here, 2 minus mu, omega k, and also I think omega k. So if you are here or here, okay, that's the condition for number 2. You are not close to this, but a bit far away, but not as far as to 2, okay, or not as far as 0. If you are here, the conclusion is that you have some lower bound of the mean curvature, L2. Okay? So you have to have some amount of mean curvature if that's the case. Either you have a hole, or you don't have like even you have just fraction of unit disk. Then you have big mean curvature, or I would say big, but at least some amount of mean curvature. Okay? Yeah.
So you did these on the ball radius 2 and radius 1. What's
Yeah.
the scaling? So I see the scaling of
Oh,
the
yeah,
ball.
scaling,
If I
yes.
want it on- if I want to do it in R and 2R, so I see the scaling of zeta. What's the scaling of H? The H is what, like 1 over that?
Certainly, yeah, 1 over r. Yeah, just it's mean curvature, so yeah. So yeah, I wrote this without any r, or you can, of course, everything is scale invariant, in fact, if you do it right, yeah. So because of the lack of time, I just normalize everything. Okay. Now, so yeah. Yeah. Sorry. No.
1 minus mu omega theta k.
Could you say?
The
So,
third line in
yeah. Third line. Yes.
1 minus mu times omega theta k get up about for the area difference between the
Yeah.
plane and the support of varifold.
Yeah.
Why doesn't be needed for the low bound of the mean curvature?
Well, you see, for example, if you don't have that, you can take t as your varifold, and if varifold is just t itself.
You mean 2 planes?
Yeah. Well, let's say one plane or one plane, then that condition is not satisfied, right?
One plane,
Yeah.
that is okay.
That's it becomes 0, right? I mean,
So the upper bound is not necessary.
or if you have 2 planes, then you have problem. Yeah. Say suppose you have 2 planes. That's going to be the difference is going to be omega k, right? So that actually that is avoiding 2 planes situation. This upper one, and lower one is also avoiding. I guess. Yeah, 1 plane. Yeah, that's right. Exactly. Thank you. Yeah. Okay. Okay. Let's see. So this is geometric Sobolev inequality. It's the name I thought is appropriate because that's sort of the things that this means. Okay. So now let me just give you a heuristic argument that heuristic is that notice that if this support is a graph, the sort of best situation, then alpha is what? This is mean curvature, so it's roughly mean curvature is like Laplacian of f. I mean, if in a linear order, and also of course you have this area element. But well, assume that the number u is small. Okay, just as a. Then well, you can think this as 1. Okay, so alpha is really like, well, okay, you have 1/2. alpha is really like the delta f square times phi t, not square. Okay. So alpha is really like W22 norm in some sense. Okay. And like C, as I explained, well, this is like a distance square, so it's really like FL2 square of the, that's what it is, okay, over ball radius 2. And also notice that this quantity, phi t square dvt, dv, minus omega k tilde. Well, this quantity is, if you think this is a graph, this is nothing but phi t square and 1 plus number phi, number phi square dx and minus, well, by definition of omega k, this is nothing but phi t square integrated over t. Okay, so this is also t. Okay, that's. By Taylor expansion, this comes out to be, well, if the gradient is small, this is 1/2 of phi t square of nabla f square. Okay, so this quantity is like a Dirichlet energy in some sense, if everything is nice. So this is really saying that if this Dirichlet energy is not too big, then you have that things. You see Dirichlet energy is bounded by sort of, you know, the right-hand side, where the right-hand side is, if you interpret it this way, isn't too bad. I mean, it's kind of reasonable. If you think about scaling, all these things that you see there is somehow a nice combination. So, this is a way that you can interpret this statement. Okay, so please think this as more like a Dirichlet energy of the graph. Okay, even though this doesn't look like it, but it is in fact, if everything is nice. So, right. Okay. So the proof of this is actually somewhat intricate, but and it's not quite explicitly written in. I mean, it is written, but with some amount of mistakes in Brakke's book, so it's not so. But it's not so clearly written. But in my paper, it's written fairly clearly. So if you're interested, please take a look. And proof, as I said, proof uses again. In fact, at this point, is you use Lipschitz approximation. Lipschitz approximation, and so-called the cylindrical growth lemma, which I don't have time to explain, but you can find it in my paper if you're interested. Okay, so proof takes some number of pages, but I hope it's if you're interested, please take a look. I think it's clearly written. And so how am I going to use this? Okay, so the way that one uses is so the idea is if your area is a bit far away from the unit disk, you have this lower bound of the mean curvature. And the nature of this Brakke's inequality is that if you have a mean curvature, area tends to decrease. Okay? Because you see, you have on the left-hand side of the Brakke's mean curvature, you have minus h square, right, in the expression. So whenever you have some amount of L2 of mean curvature, it tends to decrease the area. If you have that lower bound, it decreases the area at some fixed rate. Okay, that's roughly the idea. So if you have that lower bound, just area keep decreasing and decreasing. Now, once you approaches to this range, then the first option comes into play. Okay, either you still have mean curvature, then it keep decreasing, or otherwise you have that inequality. Okay, so Now, let's see. Maybe I don't have time to explain this, so maybe I'll just skip this computation. But yeah, I think actually this is somehow nice computation. But let's see. Maybe I should do it. So the next step is, okay. So now let me actually show you how the computation goes. This part, actually, I can use the analogy with heat equation. Okay, so with this, so I'll just skip this part, and maybe if you're interested, this is very easy to do. You can compute the dilution energy like this. Okay, you do compute this. I think everybody can compute this, and you can actually check after a bit of Cauchy-Schwarz and doing some number of integration by parts. You can actually show that this is less than. I was going to do this in Blackboard, but I don't have time. So you can actually derive this formula, this constant depending on phi, and so support of phi of f squared. Okay, you can, using a heat equation, you can derive. You can kind of imagine that this is bounded by this kind of thing. You know, you just do integration by parts a lot, and this is L2 norm of f. You can do exactly the same computation with Brakke's mean curvature flow, surprisingly, in fact. Now, integration by parts is the one that you use this formula of this guy. Integration by parts. Integration by parts, you use this is equal to trace of S dot nabla G dV. Integration by parts is replaced by this formula. And then you just do exactly the same computation. And what you can prove is the following. Is in fact, you can compute. Oh, okay. So this is actually, you should express this in integration, but you can actually prove the following. This time difference is less than or equal to minus 1/4 and h squared phi t squared dBt plus constant, well, which depend on phi t, in fact, times t perp x squared. Surprisingly, the same computation, really. Well, you need to do a bit of it. You know, you see complete, analogy, right? That is, this, as I said, is dilution energy, as I said, in a very naive heuristic way. This is Laplacian f, roughly. This is L2, okay? And you can do exactly the same kind of computation on the Brakke's inequality, and you can get this. Now, let me call this as ET, and let me call this as alpha t squared, and let me call this as ct squared. Okay? So you have this differential inequality as a result from Brakke's inequality. Okay? So you see what I was saying. If you have some amount of alpha, it just decreases energy or area. Okay? But with this extra little positive guy. Okay? But this is sort of lower order term. This is higher order term. Okay? Now, argument is really ODE argument at this point. In fact, once you have these two things, then the things you can do is that, okay, maybe I should just draw pictures. Okay, so you have this ddt of Et is less than or equal to Et is less than or equal to minus 1/4 alpha t squared plus constant times ct squared. Okay? And it turned out, I don't do that today, but it turned out this CT is actually uniformly bounded because, well, using sort of Huskins monotonicity formula, this can be bounded uniformly small. Okay, so this is something you can do, and in fact, you can make it so that this is much smaller than uniformly, say C1, which I can assume to be much smaller than alpha 1 of the lemma above. Okay, so this is actually comes from, well, tomorrow I explain this, but today, sorry, today I guess I have today another lecture. Just use Ken's monotonicity formula. I can prove this can be made uniformly small. This L2 norm is uniformly small, so I can kind of forget about this guy. It's actually uniformly small, extremely small compared to other things. Okay. So what happens is that, okay, so for simplicity, just let me drop this guy just because I know it's very, very small. So you end up having this differential inequality out from Brakke's inequality. Okay. And then what do you have? And then it gets interesting. Note that, okay, so all we have is this guy now. It's very simple. And with that inequality, okay, what can you do? So now let's say this is time. Here's minus lambda. That's the beginning, and that's the end. Now at minus okay, so minus lambda plus t1, we have this assumption that the mass or the area is less than, let's see, okay, maybe, let's say here's the 2 lambda omega k, and I know that near the beginning, this is a level of 2 omega k minus, 2 minus nu omega k. So that's this guy. And so I know at this point, at time t equal to minus 1 plus 1, it's below this line. Okay, it's below this line. That's one of the assumptions we had in the statement of epsilon regularity theory. Okay, and okay, let's write here is omega k tilde, and also I know by assumption near the end, I know that at least I have some amount of area. So nu times omega k tilde is something I wrote. So I know here I'm above this guy. Okay, I'm above that. Okay, that's assumption. Okay, so now suppose area is somewhere here. Also, maybe I should also write this. Let's see. This is I think 8/9 omega k tilde, and this is 8/7 omega k tilde. Okay, that's a sort of important range. Okay. Okay, now we are sort of almost done. Well, we start out somewhere below this point, and then what happens? Suppose you're here in this range. Okay, suppose you're in this range. What this tells you is that corresponds to either number 1 or number 2. Let's see. Well, I guess it's actually number 2. Okay, because you are away from this range, right? So you have this bound of mean curvature. Okay? The alpha is at least bigger than alpha 1. So what does this tell you? That means this E just keep decreasing at a fixed rate. So at least it has to just keep going. Okay? Maybe not continuously actually, but it could be discontinuous, but at least it has to decrease until you enter this range. Okay? So maybe it takes some time, but because it's fixed rate, it keeps going. So some amount of time it takes at least. You can estimate. Now once you're in this range, what happens? Once you are in this range, then you are in this number 1 setting, okay? Because you are, in this range. Now, if you have alpha bigger than alpha 1, it still keeps going at the same rate. But if it's less, you have that inequality. Now, what does inequality tells you? Well, let's take k bigger than 3 case. Then this it says that the alpha t, et has to be less than or equal to constant. And just let's take the first term and forget about the rest, actually, because I can kind of think that c is very, very small. So that's, you have this relationship, just forgetting about all the rest. By the way, et, yeah, just a moment. That's kind of strange. Oh, wait, maybe there's something wrong. Oh, yeah, I guess that's okay. Yeah, okay. So now then what we have is that then this means et of k minus 2 is less than constant times alpha t of square, right? That's the same thing, well, with different constant, of course. Now use that into this differential inequality, okay? You see, you plug that in, then you get this differential equality, ddt of et is less than or equal to minus 1 over 4 e to the, well, some constant, of course, constant k minus 2, okay? Okay, with some error, I'm saying. But this gives you a nice differential inequality which sends you e to 0 in finite time, okay? Because this exponent is less than 1. And you can actually estimate how much it takes to get to 0. Actually, it doesn't get to 0, perhaps, but because of the error term. But that's roughly, right, idea is that in finite time, it has to go down this sort of range, okay? Either it stays, it may stay, actually, it may stay here, but the point is, in finite time, it's in here, okay? And now you do the same argument going back this way also. So it's more like reversing time, and then you can actually show that if you are up from here, reversing in time, you know that in finite time, you are in this range. Oh, okay. So maybe I should have said that this gives you that et, well, because of the error term, you know that this is going to be c square, actually, after some finite time. Okay? That because you have some error term of c square, so you can show from this differential inequality that in finite time, this is going to be bounded by constant times c square. Okay? But notice that, anyway, so near the center of time, you get this kind of estimate, okay? But now notice that this is like Dirichlet energy, this is L2, okay? So this is like getting a Cacciopoli type inequality, okay? Near this range. So that's very roughly the strategy of getting this Cacciopoli type inequality for this one. And once you get this estimate, in fact, the end result you get is, so for this kind of argument, gives you oh, by the way, so it's very important to have this exponent to be less than 1, okay? And that exponent 2k over k minus 2 is bigger than 2 is essential importance to carry this out, okay? And so this kind of argument gives you the, at the end, you get sup of t between minus 1 to 1 of the phi t square dvt this is bounded by constant times, let's see, this well, I think yeah, some estimate like this. As I said, this is ET. So you get a sort of uniform in time digital energy bound in terms of L2. Okay, that's the kind of thing you get out from this argument. I mean, it's very rough explanation, but I think this is roughly the idea. And once you get this, you note that because of this relationship, once you have this bound uniformly in time, you get also L2 bound of the mean curvature in space-time. It's easy to get actually this bound also, h square dvt. Bounded by the same quantity. Okay? So you get also sort of W22 space-time L2 non-bound in terms of L2. So that's how you get the first Cacciopoli type estimate. And so building upon this, and the other elements that I'm not using too much is the Huskins monotonicity formula. And in the afternoon, I'll show you how you get that and also how you can use it. Okay, so that's it for the first one.